In the last lecture, we were examining the temperature field due to a point source, first in an infinite domain, where in an unbounded domain where there are no boundaries and therefore no boundary conditions to be satisfied, and then secondly in a finite domain, okay, where you had a boundary wall. Okay. And we saw that the boundary conditions can be satisfied by adding to the source, okay, which is at a perpendicular distance L from the boundary. In the same perpendicular line as the source, you add a sink on the other side. Okay. The physical domain is of course only the domain for positive z. Okay. So, that is the physical domain. There is a wall at z is equal to 0. The effect of this wall on the temperature field can be represented by removing the wall and adding a source minus q or a sink q at a distance L below the surface, okay, at a distance L below the surface of equal strength, that is of equal amount of heat generated per unit time. And if you do that at the surface itself, which is the mid plane between the source and the sink, the flux lines have to be necessarily perpendicular to the surface just by symmetry. Okay, I had shown you that. So, therefore, you can represent the effect of the boundary by just using an image source or an image sink, which satisfies the condition that the flux perpendicular to the surface is equal to 0. And this can be extended as well to distributed sources. Okay. And I had shown you how you can express the Green's function as the summation over the sources and over the sinks. Okay. Note that QV of x prime, xi prime, in this case QV of xi prime is equal to just the negative of QV of x prime, okay, because at the image the flux is just the negative of the flux at the source. Okay. So, this thing has to have a negative sign here. If I put a negative sign here and just write this as x prime, okay, this will give me the correct expression, okay, because the source strength at xi prime has to be negative of the source strength at x prime. Okay. So, I should write this as QE at x prime. Okay. And this for us defined the Green's function. Okay. This for us defined the Green's function. Similarly, if you had an insulating surface, I said that you can put a positive source at a location that is on the same vertical line below the surface outside of the physical domain. The effect of that will reproduce the effect of the boundary on the flux lines in the physical domain, which is that the flux lines go parallel to the surface, okay, at the insulating wall, because if it is insulating, there can be no flux going perpendicular to the wall into the wall. Okay. So, all the flux has to go parallel to the wall. So, this basically reproduces the effect of an insulating surface. Okay. And we had got a Green's function for that as well. Okay. In this particular case, Q, the volumetric source strength at xi prime is equal to what it is at x prime. Okay. So, it is an insulating surface. Okay. Now, what do you do for the general case? Okay. So, for a point source, you recall that I had solved del square t plus q delta of x is equal to 0, and the solution was t is equal to q by 4 pi k into the magnitude of x vector. Okay. And then I had solved k del square t plus q v of x is equal to 0 for the distributed source, t is equal to integral dv prime. Okay. So, basically this integral relation is the inverse of the differential equation. Okay. This integral relation is basically the inverse of this differential equation. and this we had done by just taking a point source, constructing a volume around it and so on. But essentially this Green's function, this integral relation, is the inverse of the differential equation in an infinite domain. Okay. In a finite domain, it will be necessary to satisfy boundary conditions. So, how do we satisfy these boundary conditions? Okay. So, let us say I have a temperature K del square T plus QV of x is equal to 0. Let us say I have a temperature field K del square T plus QV of x is equal to 0. Okay. I define a temperature field for a Green's function, okay, K del square G, okay, plus delta of x is equal to 0. Okay, K del square T plus G plus delta of x is equal to 0. Okay. This Green's function also satisfies the boundary conditions, which is identical to the boundary conditions that the temperature field has to satisfy. Either constant temperature conditions, which means that the derivative of temperature along the surface is 0, or 0 flux condition, that the derivative of the temperature perpendicular to the surface is equal to 0. Okay. So, the two kinds of conditions are, okay, the Dirichlet conditions Gd at the surface xs is equal to 0, or Gn, okay, or the flux is equal to 0. Okay. So, if I have some domain where I want to find out what is the temperature field, okay, if I have some domain where I want to find out what is the temperature field, I could specify the temperature at that surface. Okay, that is one possibility. Okay, okay, that is this one. Okay, I specify the temperature of the surface and subtract out that temperature from the temperature everywhere, so that the temperature, the redefined temperature at the surface is identically equal to 0. And the other way to do that is to specify that the normal flux at that surface, okay, the flux perpendicular to the surface is equal to 0, which means that the temperature variation in temperature perpendicular to the surface is equal to 0. So, these are the two possible conditions at this surface x is equal to xs. Okay. Okay, so, these are the two possible conditions at the surface x is equal to xs. Okay. This is for the Green's function. Okay. I also have boundary conditions specified for the temperature field. This Green's function is just an imaginary construct in order to determine an equation for the temperature field, and I will show you how this is done. Okay. So, let us define the integral I is equal to integral over the volume of the source. Okay. The integral over the volume of the source of the divergence with respect to the source point, not the observation point. Okay. Here the source point is x prime. Okay. So, let me write that somewhere. Okay. The source point is x prime and the observation point is x in the analysis that I will be doing. And whenever I write down gradients, those are either with respect to the source point, in which case there will be a prime, or they are with respect to the observation point, in which case there will be no prime. Okay. So, I take the divergence of g of x minus x prime, okay, del prime t of x prime minus t of x prime times the gradient of g of x minus x prime. Okay. I could simplify this in two ways. Okay. One is of course to use chain rule for differentiation. Okay. If I use chain rule for differentiation of the terms within the brackets, I will get using chain rule for differentiation. Okay. And you can see that these two terms are both identical. Okay. These two terms are both identical, and this will be equal to integral dv prime into g of x minus x prime, okay, del prime square t of x prime plus t of x prime and for these two terms, okay, I substitute from these governing equations. Okay. Okay. Yeah. So, this will become integral dv prime g of x minus x prime, okay, and del square t is minus qv of x prime by k, okay, plus t of x prime, okay, into minus delta of x minus x prime by k. So, these are the two terms after substituting from the governing equations. Okay. And there ought to be a negative sign here. Yes. Okay. The second term here you can easily see is just equal to t of x by k. T of x prime delta of x minus x prime integrated over x prime is just the delta function. Okay, so, that is just equal to t of x minus integral, I take the k outside, okay. So, this is one simplification, okay, of this integral I. Okay, this is one simplification of this integral I. One can do a second simplification, that is using the divergence theorem. Okay. Divergence of something integrated over the volume is equal to the unit normal times that same thing integrated over the surface from the divergence theorem that we have already seen. Okay. This is n dot g of x minus x prime, okay, So, both of these are equal. okay, both of these are equal. Therefore, I can multiply throughout by k and equate these two and get an expression for t, okay, is equal to integral dv prime g of x minus x prime. Okay. Plus additional terms that arise due to the boundary conditions on the surface. Okay. Plus additional terms that arise due to boundary conditions on the surface. Okay. A prime on the unit normal, because the unit normal is with respect to the source location, okay, for the surface bounding the entire volume, okay, for the source location, okay, n prime dot So, this is the temperature field, okay, the solution for the temperature at a given location x due to the sources at the location x prime, where g is the Green's function, okay, and qv is the source. Okay. You recall that this first term here was what we had obtained when we just had a point source in an infinite medium, or a distributed source in an infinite medium, okay, where the distributed source was qv. For that distributed source, we got only this first term here, and that we had solved in order to get the temperature field in an unbounded system. The second term here is what you get due to the boundary conditions on the surfaces. Okay. The second term here is what you get due to the boundary conditions on the surfaces. And this can be, and so this function g has to be chosen. Okay. So, the simplest way to solve this, of course, you can solve this equation as it is, but the simplest way to solve this is to choose the value of g in such a way that this second term is identically equal to 0. Okay. So, you can consider two cases. Okay. One is constant temperature conditions. At the surface, that is, you choose, that is, T of x prime is equal to 0. Okay. If you have a constant temperature at the surface, then T of x prime is identically equal to 0 if you subtract out the surface temperature. So, if that is the case, you can see that within the surface integral, the second term is identically equal to 0. Okay. And therefore, you can choose g of x minus x prime is equal to 0. So, that the first term also becomes 0, and then you get the simple equation for the temperature field. Okay. That is what we had done for the case where you had a perfectly conducting wall. The temperature on the wall minus T infinity was identically equal to 0. Therefore, we had chosen the Green's function in such a way that that also had a 0 value at the wall. Okay. So, that this, in that particular case, you recall we had chosen g of x minus x prime is equal to So, when chosen in this way, the temperature is identically equal to 0 for g as well. Therefore, the first term within the square brackets on the right, that is also equal to 0, and therefore, the temperature boundary conditions are identically satisfied. Okay. So, if you have temperature specified to be 0 on the surface, you choose a Green's functions which also has a 0 temperature on the surface. Okay. 0 temperature, I mean a constant temperature, because you can always subtract out a constant, okay, from the total temperature. The second possibility is 0 flux. Zero normal flux at the surface. Okay. That is, n prime dot the gradient of T of x prime is equal to 0. That is the second possible condition. Unit normal times the gradient of the temperature is equal to 0. In this case, within the surface integral here, okay, the first term on the right is identically 0 because n dot grad T with respect to the source location is identically 0. Okay. Therefore, you can choose n dot this is equal to 0. Okay. And if you do that, the entire surface integral becomes equal to 0. That particular Green's function has to be substituted into the volume integral on the right side, okay, in order to find the temperature field. Okay. So, and that was what we did in the case of an insulating wall. Okay. You recall we had chosen g of x minus x prime is equal to 1 by 4 pi k into x minus x prime I am sorry, here it should be a negative sign because the temperature has to be 0. Okay, kindly note this. This was a negative sign because we had a source and a sink for a conducting wall, whereas for an insulating wall we have two sources. Okay. So, by this appropriate choice of the Green's function, we can ensure that all boundary conditions are satisfied on the surface. Okay. So, this is the method of Green's functions. Okay. So, I told you that when we have a point source in an infinite domain, okay, the inverse of that is that this temperature equation. Okay. The left side is a differential equation and that can be solved to obtain the right side for a point source, because this is a localized source. It is present only at the location x is equal to 0. For a distributed source, the equation is k del square T plus the total volumetric, the total heat generated per unit volume per unit time, volumetric source QV is equal to 0. Inverse of that is the integral relation on the right side, okay, integral over the volume of QV of x prime times 4 pi k into x minus x prime. Okay. These are both in unbounded domains, okay, where there is no boundaries, where it is not where you do not satisfy boundary conditions because it is an infinite domain. If it is in a finite domain, okay, that is if you have, okay, that is if you have k del square T plus QV is equal to 0 and boundary conditions. Okay. The solution is T is equal to integral dV prime QV of So, that is the solution, okay, in a finite domain where this Green's function satisfies the appropriate boundary condition, okay, where the Green's function satisfies the appropriate boundary condition on the surfaces. So, this is the formal extension of the solution of the heat conduction equation for an arbitrary system where you have to satisfy boundary conditions on boundaries. You could have mixed boundary conditions as well, conducting perfectly conducting surfaces on some boundaries and perfectly insulating surfaces on other boundaries. And in those cases you have to specify the Green's functions to be conducting and insulating at the appropriate boundaries in such a way that this integral is identically equal to 0, okay, that this integral of the second term on the right hand side is identically equal to 0. Okay. So, with this we complete our discussion of the diffusion equation. We had started off by separation of variables solutions for Cartesian coordinate systems, and then a separation of variables solution for a spherical coordinate system. The separation of variables solution in a spherical coordinate system has multiple interpretations. One is just the separation of variables procedure, which gives you a temperature of the kind T is equal to sigma n is equal to 0 to infinity, sigma m is equal to minus n to n, a n m which we also wrote it as sigma n is equal to 0 to infinity times the spherical harmonics. Where these are orthogonal. The second one is the complex conjugate, okay, because these are complex functions in general. Minus m prime is the complex conjugate of y m prime, okay, is equal to delta n n prime. Non-zero only if n is equal to n prime and m is equal to m prime. These were the spherical harmonic solutions. Each of these terms, this expansion, I had related to combinations of sources and sinks. Okay. The first term was just a point source, second term was a point dipole, source plus sink separated by an infinitesimal distance such that the product of the distance and the energy generated per unit time is finite in the limit as the distance goes to 0. Those were the dipole moments, 3 of those aligned along the 3 coordinate axes. The next one was the quadrupole, 2 sources and 2 sinks in such a way that net source is 0, net dipole is 0. Source decreases as 1 over r as r goes to infinity for the decaying harmonics and is a constant for the growing harmonics. Dipole decays as 1 over r square for the decaying harmonics, increases proportional to r for the growing harmonics, and similarly the quadrupole goes as 1 over r cubed and r square for the decaying and growing harmonics. And then we had used a delta function source, got a solution, and then got a solution for a distributed source by superposing multiple delta functions in an unbounded domain. And further we had used the method of images to satisfy boundary conditions, and finally I had shown you the Green's function formulation, which can be used to satisfy boundary conditions on any boundary surfaces where boundary conditions are satisfied. So, with this we have completed our discussion of the diffusion equation, solution of the Laplace equation or the Poisson equation in Cartesian and spherical coordinates. And in the next class we will discuss forced convection in the limit of high Peclet number, where the ratio of convective and diffusive transport is large. Okay. That is the direct opposite of the limit we have considered here. Here we have considered low Peclet number, convection is small, we have neglected convection altogether and we have solved the diffusion equation. In the next lecture we will consider high Peclet number. Convection is dominant compared to diffusion. However, close to surfaces diffusion cannot be neglected because transport perpendicular to the surface is necessarily due to diffusion. That we will start in the next lecture. I will see you then.